Okay, cool. So there is page 20 in all of its glory. Take a look. I want to see how you did. Feel free to just kind of bounce back and forth between your work and mine. 4, 5, and then 6, 7. And then we'll ask any questions that you might have before we move on to page 21. So take a minute, look at how you did, look at what I did. If you got them right, then yay. If you got them wrong and you're like, oh, I know what I did, then cool. But if you're not sure, then ask questions for sure. And remember, any of the infinity or negative infinity answers, so like 5a or 6d and e, those can, of course, be written as does not exist instead. Okay, that's a perfect answer. So I'll give you a minute, check that out. Okay, thoughts, questions, worries, or general happiness that you're doing really well? Got it? Some okay, some better. Okay, cool. Yay, smiles. I like those. Okay, good. Any questions? Nice. Any questions I can answer before we move on a little bit? Because this is kind of, for now, us leaving graphs behind a little bit. But I thought these were really good ones to kind of show you both sides of this. You know, some of the trickier stuff where we're heading towards an asymptote or we're heading towards a hole, or some of the not so tricky ones, like number 5, part F. Yeah, it's a limit, but I mean, look at 5F, right? The limit as x approaches 3. Well, like, there's no hole there. There's no gap there in the small space nearby. Now, I know there's something happening at 4, but for us, 3 and 4 are really far away from each other. In calculus, sometimes that's the truth, is we want to be really, really close in the space nearby, and things are really nice and continuous around 3, which we really like. Same thing for like 6a, right? Go to 0. Okay, cool. There's a point there. I don't have to worry so much about finding a tricky limit if there's nothing breaking this graph apart in really strange places right near like x equals 0. Sure, there's an asymptote at 1. I know there's a horizontal asymptote for our end behavior, but that's way over there, right? And 1, so far away from 0, right? Super far away. So this kind of touches on all of that, which is really nice. So hopefully that went okay for you. And of course, we will continue to practice with stuff like this. Let's look at 8, 9, and 10. I'm going to bounce around a little bit, but this started to get us thinking just a little bit differently. And I had a bunch of people stick around yesterday, which was great. So you'll hear kind of the same explanation for some of these that you maybe have heard yesterday. But in case you missed it, I want to make sure we're okay with 8, 9, and 10. So they give us a picture of a graph, and they want us to figure out, are things true or are they false? For number 8, right, as x approaches 1, what's the limit, right? Are we headed towards 2? Well, from the left, sure, but not from the right, right? As we go up this way, sure, I'm headed towards 2, but as I travel along the function this way, I'm headed towards that hole, so this one would be false, okay? And they wanted us to explain why, right? For statements that are false, explain why, so something along the lines of, like, because, I don't know, like you can just say that like the limit doesn't exist, or you can tell us why the limit doesn't exist by saying that the limit as x approaches 1 from the right is actually equal to 1 and not 2, right? Something like that I think would be great. You can use words, you can use symbols. Either one's fine by me. Okay, I'm going to skip down to 10 just for now before I go back to 9. But them asking, you know, does the limits as x approaches 2 exist or not? They're telling us it doesn't, but it definitely does, right? This statement is false because, and you can say it in words, because the limit equals 1, right? Because the limit from both sides are the same. And if you tell me that the limit exists, you are saying that the limit from the left is the same as the limit from the right. Okay, that's kind of implied in what you're saying, because we now know the limit existence theorem, right? We learn theorems and then we rely on them to kind of say all the things we need to say. 9 was a little bit trickier, right? Because 9 asks a very different kind of question. 8 and 10 were about stopping at specific x values and deciding whether the limit existed or not. Number 9 kind of changes that a little bit. And this is kind of like the next step in calculus is considering not just one space where the limit exists or doesn't, but finite spaces, right? In this case, between -1 and 1. And they don't include those endpoints, okay? And there's a reason why they don't include those endpoints. So I actually want to think about that part first. Like what's actually happening at -1, what's actually happening at 1 for the limit? Well, the limit for 1 clearly does not exist. We already just kind of talked about that with number 8, because the limit from the left and the limit from the right are different. So I know I can't include 1, and so I'm glad that they did it, right? This open interval right here, and they said on the interval, so I know it's not a point they're talking about, but they're saying, okay, from when x is -1 to when x is 1, but don't include those endpoints. So not including 1, okay, good, at least we're good on that side. And what about at like -1, right? Well, as I approach -1 from the right, yeah, there's a limit there. It's 1. Cool, that looks good. But when I try to approach -1 from the left, I can't. There's nothing over here, right? Calculus happens in motion. These limits are about like getting close to that y value as I travel along the function over here, but I can't do that. And so the limit from the left, it doesn't exist because there's nothing for me to do. I can't move along a function if there's no part of the function over there. So I'm very glad that they did not include -1 in this statement if I want it to be true. Because if they did, right, if it looked like this, right, with the hard bracket there, false, doesn't exist because there is no limit from the left. Or if it looked like this, right, nope, definitely false because, I mean, I just said it in part 8, right? The limit from the left is different than the limit from the right. So good, at least we're now just kind of looking in between, okay? And so that's what we kind of just want to think about is, all right, well, let's look at some points in between and see how we feel about those limits existing. I don't know, like at 0, right? Does that limit exist at x equals 0? Are you approaching the same y value from left and from the right? Sure, absolutely, right? Because there's no gaps, there's no holes, it's nice and continuous. That's awesome, right? Same thing at like 1/2, right? There's a nice point there wherever it is. I don't know what it is, but I know that in the space nearby, there's nothing screwing up my chances for that limit existing. Limit from the left looks great, right? Limit from the right. Even something like -0.9, right? Something like that, pretty close to -1. Limit definitely exists. Why do I know that? Because I can go to the right, obviously, I got plenty of space to the right to be able to approach it from the right. And there is space between negative 0.9 and negative 1. There's a function there, right? There's part of a function there. And so if I can get myself onto the left of negative 0.9, then I can approach it from the left, okay? So I feel pretty good about that one. And so let me ask you this. Well, what if it was like negative 0.99? The question you want to be asking yourself is there space between negative 0.99 and negative 1? Are there points in between those two where the function exists? Is it continuous in that space? Then the limit exists. Because there's nothing holding me back from scooting just a little bit over and moving myself along. And I know the space is getting smaller, but there's still space. There's still measurable space. Okay, well, what about like negative 0.99999? The point exists. I can certainly go to the right of that. And as long as I have space to the left of that, I'm good to go. So is there space to the left of that number before you actually get to negative 1? Sure, it's super tiny. We're getting smaller and smaller by the second here, but there is space. And although it's super small, I can still approach that number from both sides because I could just go to here to do it. Oh, can I get to the left of that? Sure, because I can go to there. And I can go to there, and I can go to there, and I can go to there, and I can go to there. And what this idea is kind of bringing up to us is that open intervals give us a lot of freedom because I never actually have to get to negative 1, but you can pick any number you want in that interval, and I can get closer by doing this. And I can get closer, and I can get closer, and I can get closer. Because they're saying for every value of C. So that means, go ahead, pick one. Can you find the limit there? Sure, because I can get closer on both sides, right? I can kind of fill in those gaps on either side. So this is true. That statement is true, right? Block off those endpoints and it automatically becomes false. But that open interval gives us so much freedom. And you're going to see that we are going to rely heavily on open intervals for this exact reason. Because in a finite space, there are an infinite number of points. Because I can always get closer to that endpoint by cutting the distance in half, right? By going halfway between whatever point you give me and the end, right? Cool. So hopefully that conversation makes sense and that starts to sink in for you. Okay. All right, let's do 11 and 12 if you're ready. And here's where I want to hear from you a little bit. And if we were in school, this would be me handing you the reins and somebody would actually come up here and draw this. So keep that in mind as we start working towards getting back next week. We'll talk about what next week looks like a little bit tomorrow, and I'll talk about what tomorrow looks like very soon. But I would love to hear from anybody. You don't have to give me the whole thing, but maybe you can if you feel pretty good about your graph. Let's start with just 11. Tell me how to draw what you drew yesterday that looks at all three of those statements and your picture is true. Does anybody feel confident in what they drew well enough to take a shot and tell me how to draw it up here?
Sure.
Yeah, go for it.
So I had a hole at 1, 3.
Cool.
And then I had a line just coming from the left-hand side from the negatives and swirling into that. Yep.
Cool.
And then I had a point at 1, 1.
Okay.
And then I had a hole at 1, -1.
Okay.
And then I just kind of went off to the right with that line.
Ta-da, check, check, check. Works out, right? Because as we approach 1 from the left, we're going towards 3. As we approach 1 from the right, we're headed towards -1. And as we actually find the point, it's sitting there at 1, 1. I think as long as you have a hole there, and a point there, in general, your graphs are probably correct. So how you kind of drew these tails, I guess, that approach those holes are up to you, as long as it's a function. Right? As long as you drew a function, I bet your graph looks good, right? So you could have done this, right? You could have done this. You can draw kind of whatever you want. as long as didn't do this, right? You can't draw things that have points stacked on top of each other. So get rid of all the non-function, or just make sure it passes the vertical line test, make it look something like that, and it looks good. Well done. Nice job. There you go. And sometimes it's easier to just like with this one, it might have been easier to start with a point, right? Say, okay, where do I know there's got to be a point? Oh, okay, 1, 1, right? That's what f of 1 equals 1 tells me. And then, all right, well, if I have a different limit than the actual point, I better put a hole there instead, right? Because we're headed towards a number, so it can't be an asymptote. That's headed towards infinity or negative infinity. So anything like that, I think would be great. I like it. All right, what about 12? Let's hear from somebody else that maybe has some ideas. Now, the thing that's different about 12 than 11, like all of the action with 11 happened at x equals 1, right? The limit, and the value all at 1. With number 12, you've got a couple things happening at -2, and then a couple things happening at +2. So we kind of have to deal with those two sides of the graph separately. So somebody else, tell me something about graph number 12 that you feel pretty confident in.
I put a vertical asymptote at -2, and as the graph approached from the left, it went down, and as it approached from the right, it kind of squiggled and then went up. And at 2, I put at 2 negative, no, 2, 2, I put a hole.
Okay. Now, did they tell us where that hole had to be? Like, besides it like actually existing at 2, does it matter if it happened at like a y value of 2 or a y value of 1 or a y value of 4? Or, no, because they didn't say what the limit was. They just said that the limit existed, but that the point didn't. Right, so how you approach that point was pretty crucial. Like we had to approach some hole at x equals 2 from both sides. It just didn't matter where the hole was because they didn't tell us what the limit was like they did with number 11, right? They said the hole is definitely at 3 up here and definitely at -1 down here because those are the limits from the one side versus the other. This one just says that the limit doesn't matter where it exists, it just exists somewhere. So pick a spot, put a hole there. As we approach it from the left, we're going down towards negative infinity. As we approach it from the right, we're going up towards positive infinity. Looks good, okay? However you want to do that, okay? Whatever that graph looks like, just draw yourself a function with the key characteristics being definitely a vertical asymptote at x equals 2, because that's the only way we can have limits that head down forever like the first one or up forever like the second one. And so they really didn't have to tell us that f of -2 is undefined because you have that kind of action as we approach it, right? Headed down forever or up forever. Cool. So if your graph looks something like that, definitely need a hole at x equals 2 somewhere and just approach that hole from both sides. And a vertical asymptote at -2 where we go down from the left and up from the right. Okay. And for 13, that limit, of course, definitely does not exist because, I mean, want to know why it doesn't exist? Because those two things are true, right? Because the limit from the left is not the same as the limit from the right. Even though the point exists, right? The function has some sort of discontinuity. And we'll actually start describing discontinuities differently, like what's happening at -2 versus what's happening at 2, two different types of discontinuity that will lead us to two different kind of actions in calculus, which would be cool. Sweet, so there you go. There's homework 1.1 in the flesh. Any questions before we do a couple things? I gotta plug in my computer before it gives out on me. Okay, cool. All right, then let's backtrack a little bit because I know we skipped over some tables. I believe page 16 is where I want to be. Is that right? Yes, page 16. Okay, so for the time being, we're gonna just focus really briefly, like 15 minutes would be great, on just looking at a couple of these tables here on page 16. And what I wanna kind of set you up for success with is that when tables are given to us like this, we're just kind of stuck with whatever we've got. But when we design our own tables in the upcoming chapters, we get to pick whatever x values we want when they give me a function to go with it. And we'll design them to tell an easier story to read. Graphs are super easy because I see the whole thing, right? And if you ask me points that I can see, then I can get as close as I want. I can tell if things are defined or not. I know what the graph looks like. And as crazy as the graph could look, if I have the visual, I can really, and I mean, you guys just did it, right? We can really wrap our heads around this idea of evaluating functions versus evaluating limits and all of the differences and dealing with the funkiness of asymptotes and holes and breaks and weird gaps and function not even existing in spaces, all that kind of stuff, okay? When they limit us to just a table, we're kind of stuck with whatever they've given us. And so what they're going to do, and when I say they, a lot of times here moving forward, I'll be talking about like College Board and thinking about their AP mindset. What they like to do is hide important information in plain sight. And I am speaking directly to this first table here. And I bet what happened is your eyes jumped right to the table. And that makes a whole lot of sense because that's where most of the information is. But there is also one really, really important piece of information that is buried in plain sight in the words leading up to that table, where it tells us what kind of function it is. Because having some crazy looking piecewise function all over the place with holes and asymptotes, it's really hard to define that function nicely. When we look at tables, a lot of times what they'll do is they'll just pick one nice, simple kind of function, not some smashing together of a whole bunch of different ones like a lot of these graphs were, right? This is exponential, okay? And so what we need to have is kind of a basic understanding of what's going to happen with exponential functions. Because if I know what to expect from them, then I know what kind of limits I might be running into. And so the thing that we want to think about is, what is the domain in general for an exponential function? Because if I'm expecting holes or if I'm expecting asymptotes, then I know what kind of limits I might run into, right? Limits that maybe don't exist, or spots where the limit exists but the function doesn't, or whatever it is, right? And so let's think about it, right? Think of like plain old simple exponential function. 2 to the power of x. 3 to the power of x, 1/2 to the power of x, -4 times 5 to the x plus 3, whatever, right? Where the only spot where the x is going to go is up in the exponent. So pick a simple one in your mind, 2 to the x, right? Is there anything holding us back from dropping in any x value I want up into that exponent and getting a number back? Like, is there any restriction on the domain for an exponential function? Like, and this is just an example. This is not this graph, but like just to think about 2 to the x. It's an x. My goodness, it just gets worse. Can you plug in any number you want there and get a number back? Of course, which is why your domain is all real numbers. And if your domain is all real numbers, there are no holes, there are no vertical asymptotes, there's no weird breaks. Exponential functions have a very important property that makes finding limits so easy, right? They're going to look like this, potentially, right? Or they're going to look like this, right? Or they're going to look like this, or they're going to, what's the other one? What am I missing? Oh, they're going to look like that, right? No matter what. I tried to switch colors on you so you can see that these are 4 different graphs. This is not 1, this is not 2. These are 4 different possibilities for what exponential functions look like. how would you describe every single one of those 4 graphs, knowing that their domain is all real numbers? It makes limits so much easier to deal with. One magic word.
Continuous?
Continuous. All exponential functions are continuous. And if your function is continuous, then the value of your limit and the value of your function, they're just going to be the same. I don't have to worry about like, oh, there's a hole here, but the point's down there. Oh, so my limit is different. Or there's an asymptote here, so now the limit doesn't even exist. None of that really we have to worry about when going to like a specific x value. All right, go to 0, go to 1, go to 5, go to negative a million, go to pi. Whatever the value of the function is, makes it a whole lot easier. Now, so that's very, very nice. Knowing that it's exponential tells me that my function is continuous. And that this table, although it's only a collection of 7 points, should be enough to kind of lead me towards the right answer. Now, the other thing that we want to remember about these kind of functions is that although there's no holes or vertical asymptotes, what we do see is that they all kind of trend in one direction or another. Like on one side of the graph, it's going to like either head up forever, right? Or head down forever. We've got this divergence, right? We are not heading towards a number. We're either going to go up towards positive infinity or we're going to go down towards negative infinity for sure. But on the other side, whichever side it is, it starts to flatten out, right? Because every single exponential function has a restriction in the range, right? They don't go up and down forever. There's something that's going to exist on these graphs for end behavior on one side or the other. Like, and see if you can kind of put that into words. Like, what is that visual piece? What does that end behavior look like on one side of an exponential function guaranteed? Because it's going to level out, because it's going to not diverge, it's going to converge. What graphical element do we always have to draw in for an exponential function? Because they level out. Exactly. There's going to be a horizontal asymptote somewhere on these functions, on one side or the other. That's what that end behavior is going to look like. And if we know those kind of things going into this, it makes kind of reading these tables a little bit easier. Okay, and so let's just walk through. Now that we have that reminder of what exponential functions are going to look like, okay, now let's go to negative infinity. Well, I really can't do that. I can go to -9, right? But when we talk about limits, I want to kind of see what the trend looks like as I do that, right? So whether you take your eye gaze from, from -1 or from -3, just kind of move it along the table in that x direction. What we try to see are any trends in the y direction. Are we headed towards a number? Are we converging somewhere? Or are we headed either up or down forever? Are we diverging and headed towards infinity or negative? So like take a look at the sequence of the numbers, right? Limits are about kind of following patterns and seeing what we see, right? So, okay, the numbers for y go 3, 9, 33, 513. Does this seem to be converging onto a single number? Or what does that trend of the numbers kind of lead you towards? 3, 9, 33, 513. Where do you think we're going to go? If you had to infer something from the data in this table.
Infinity.
Yeah. This is getting bigger and bigger and bigger, okay? And I know that that's going to happen on one of these sides. And so I feel really confident in that answer because I know exponential functions, or I know polynomial functions, or I know rational functions, or I know sine, or I know, having that background. That's why they called it pre-calculus, because now all of that knowledge in those first 6 chapters or whatever we could do, it's all going to come back because we have a kind of a picture in our mind of what this stuff looks like. Okay. All right, I want to skip to D just for a second because we talked about end behavior on the left side. Let's talk about end behavior here on the right. like follow the trend towards infinity, right? And when we looked at graphs, right, there was a left edge and a right edge. And so when they asked us to go to negative infinity, all I could really do was go to the left edge and just kind of see what happens. Same thing here, right? If I'm just going to go towards infinity, I'm going to go to the right edge of the, not the graph, but of the table, and just kind of see about what might be happening. Okay, 9, 3, 1.5, 1.125, 1.125, and then 1.002. What does it look like we might be heading towards, knowing the knowledge that on the left side, we just went up forever?
Negative infinity.
So remember that your exponential functions on one side will diverge and head up or down forever, but on the other side, somewhere we have to head towards a horizontal asymptote. And if the trend in your numbers was like, okay, 3, 0, -10, -100, -5,000, yeah, that really feels like I'm dropping down very quickly. But take a look at the trend in these numbers. 9, 3, it's like a difference of 6. 1.5, okay, a difference of 1.5 there. 1.125, okay, now we're just in the decimals. 1.002. Like, does it really feel like we're going down really quickly? Or are things starting to level out a little bit and starting to converge?
It's getting closer and closer to 1.
And I know we're not ever going to get there, right? I don't know if you could pick it out, but this is that graph. On the left, going up forever, and on the right, starting to level out, okay? And so just kind of having that basic knowledge of exponential functions doesn't really seem quite so basic now, because now we're dealing with these infinite limits and all of the stuff that's happening. So, but the best way for me to like envision that limit actually like getting closer to 1 is that although like my x increments, you know, from -3 to 1, so a difference of 2, from -1 to 1, difference of 2, from 1 to 3, a difference of 2, and then from 3 to 9, even a bigger difference, a difference of 6, the change that's happening in my y values is getting smaller and smaller and smaller. And when you start to notice like big changes in your y values, that is my feeling of divergence. I'm taking off, I'm growing without bound in one direction versus the other. Or that feeling of convergence, that the difference in my numbers are getting smaller and smaller and smaller as we take kind of these regular steps along the graph. So I feel pretty confident that that limit right there is 1, because I think there's probably a horizontal asymptote at y equals 1. Okay? But for B and for C, they're just saying, hey, go to -3. Go to 1 and see what feeling you have about doing that, right? What feels right about trying to approach not infinity, not negative infinity, but just some x values, right? And they're two-sided limits, right? They're just plain old limits, so I have to approach them both from one side and the other. Right? I'm going towards -3. I want to kind of see what's happening there. Well, it's exponential. There's no gaps. There's no holes. There's no asymptotes. I feel really good that the value of the function and the limit are going to be one and the same. Okay, so as I head towards -3, okay, 5, 13, 33, 9. 1.5, 3, 9. Yeah. And I'm not getting super, super close. You know, I'm not at like -3.5 or -3.1 or -3.001. That might be a better table to give me that better feeling about getting closer and closer to 9. But that'll be up to us to create better when we do it ourselves. But knowing that these things are exponential makes that, it takes some of that guesswork out of saying, oh, you want to go to 1? Okay, let's just go to 1. Right? If your function is continuous at a certain point, then don't worry about like the trickiness of limits that happen around those weird spots. Like, yeah, 1.5 sounds great, right? Why? Because that's the y value at that same spot. And we love that. Like, as nice as it is to like wrap your heads around the crazy looking graphs 4, 5, 6, and 7 with all the weird stuff happening, calculus doesn't love weird stuff. We like nice stuff. I want things to work out really nicely. I want things to be continuous and smooth and curvy and functions and nice and, you know, unlimited domains and great ranges that don't have weird things happening in them if we can. And so exponential functions kind of fall into one of those nicer categories, right? Nice and continuous, domains infinite. Sure, the range is restricted because of that horizontal asymptote somewhere, but I can count on that, and I know that for sure, okay? But, like I said, when we design our own tables, we'll make them even easier to read. Oh, you want me to go to you want me to go to 1? Okay, then I'm going to go like 1.5, 1.1, 1.01, 1.001. I'm going to get super close from this side. And same thing over here, like, okay, 0 and 0.5 and 0.9 and 0.99 and 0.999. Like, we're going to really get close. And that'll give us a much better kind of feeling about the y value that we're getting close to. Okay? And the table below this kind of starts leaning in that direction, right? If you look at this table down here, do not overlook the fact that we are looking at a rational function. That first piece of information now changes my whole mindset completely. These graphs are probably not continuous everywhere, right? Our domain is not negative infinity to infinity. There's probably going to be a hole, a vertical asymptote, or maybe both, or maybe multiples of each, right? They didn't give me what the function actually is, but they told me what kind of function it is, right? We've got some spots along the way where this graph is undefined. And if it's rational, I know the two ways that could happen, right? I could get 0 over 0 and could give me a hole by plugging in either a -1 or 2, right, whatever it is, or I can get an asymptote by getting something else over 0. Now, but I don't have the function actually to look at. But what I do have is a table of values that tries to speak to the motion of that function in the spaces nearby. So knowing what I know about rational functions is going to help me out a lot, right? Knowing that I could be looking at a hole where I'm going to approach the same y value from both sides. Like, look at the space nearby 2. It's no coincidence that they gave me 2 to be undefined, but they also looked at 1.999 and 2.001, right? 1/1000th away from either one, and look at the y values that go with those, 0.333 and 0.334. Now, welcome to calculus, where 3 decimal places is all we'll ever need to do to round, but we always want to write the right answer if we can. And so if either of those were actually 1/3, they would write 1/3, right? But we can tell that that's what we're getting very, very close to. 0.333 on one side, 0.334 on the other. Now, they didn't look at like 2.1 or 2.5 to give me more of that feeling of inching closer to that spot. So we have to kind of jump a little bit to conclusions with something like part D and say, yeah, I have a feeling that we're getting pretty close to 1/3. Right? But again, we have to kind of deal with the best that we've got, which is this right here. Right? The other thing that we have to remember about rational functions is that they will always have some kind of end behavior, right? Either a horizontal asymptote or an oblique one, okay? And that horizontal asymptote is going to be the same on both sides, right? Our end behavior was always, okay, we're going to head either up or down towards that horizontal asymptote, right? So we've got end behavior on one side and the other that I feel kind of good about, right? At these really big x values, -1000 and +1000, look at the y values, 1.002 and 0.998. There's a reason why they're giving us those specific XY combinations to give us a clue that the trend that's happening, part A and part E, is that we are approaching the same y value on either side. So we're not oblique here, because then we'd head up, like our numbers would just get like big or small in the positive and negative direction. No, it looks like we're headed towards 1 for both of these, right? Let me go back to this. And so hopefully that thought process is starting to sink in a little bit. And we will definitely have practice working with tables a little bit more. Tables are the least important out of the 3 kinds of ways we can look at functions, right? Graphical, tables, and what we'll do here in a second, actually looking at the functions themselves, kind of the algebraic side of things. Okay, and then looking at B and C, like what's happening as we approach, -1 from the left, and what happens as we approach -1 from the right. Well, they didn't really do a great job of getting me close to -1, like over a period of like a handful of points. They go from -1,000 to like negative almost 1, right? -1.001. But what it shows me is a y value on one side of 2001 and a y value on the right side of -1,999. Those are not close to one another, right? And so compare that action around an undefined spot like we had at 2 to this one that we have around -1. Totally different things happening in that space, right? These y values 1/1000th away on either side. We're literally 1/1000th away with the y values. These are 4,000 boxes away from one another, okay? That is not headed towards a hole. Can't be, right? If you are so close to -1, but your y values are so drastically different, the only thing that could be happening there instead, it's got to be an asymptote, right? So from the left, I feel really good about saying, yeah, we're headed up towards infinity, or just does not exist, right? From the right, absolutely, I feel really good about me heading down towards -infinity because of how far apart those numbers are, but how close they are left and right, the x values that got you there. And so, does that limit exist? Of course not. Part F there, what happens as you actually approach -1? We're not headed towards a single y value, so that limit does not exist. Okay, so anything in red right now could certainly be does not exist. But if you want to tell a slightly better story with those one-sided limits, go for it. Okay, thoughts on any of that? First day with tables, so if stuff didn't quite sink in, don't worry, we will definitely practice with them a little bit, but they are the least important of the 3, okay? But I want to get to that third one right now before we head out. So anything else, page 16? All good? Okay, then let's jump a little ways. Go to page 22. Okay, we're gonna skip some of the extra practice in there because we've done a lot of this stuff with graphs, which is what most of this is. We'll skip some of the table practices ones that were on page 19, and we'll get ourselves right to here. Okay. Let's see if I can scoot in like just a little closer. Let's go right to, yeah. Okay, so look at the title on the top of page 22. Okay, understanding the limit is what we've been doing this whole time, but now we're going to take an algebraic approach to it. And so they kind of get us into this idea by having us look at one function first, right? Some kind of complicated absolute value function. Now, I don't love this graph over here because although like they have the arrow over there on the right and they graphed it really well, they stopped the graph right here and they put an arrow. I don't really like to stop my graph in the middle of the graph paper if it's going to keep going. Like I would keep, like if I were actually sketching this graph myself, I would definitely keep that going so that my arrows happen on the edges, the left edge, the right edge, the top edge, the bottom edge, wherever it is. That's a more complete graph for me, even though maybe some of the values that they're looking at don't really, go left of -2. Why not? Just, show me the whole graph. So, but let's think about what they're trying to get us to understand here. Look at that graph. They gave us the function now, which is even better. So now I can put the two together. I can compare things graphically. I can compare things algebraically. And my graph and calculator's got a table, so I can really put all 3 of these ideas together if I really needed to. But what is so nice about that blue graph that we yearn for in calculus. There's one characteristic that I want to be true about a graph. If I want limits to be really easy.
It's continuous.
Yes, this graph is continuous, and continuity opens so many doors, just wide open, just bust them all open, and things are so much easier because now the confidence that I have in my ability to evaluate limits really boils down to, well, the limit and the value of the function are going to be the same. I don't have to worry so much about, okay, I can get really close to it, but I can't actually, go to the point because maybe it's a hole or it's an asymptote, or maybe there's no function there at all. The domain of this is infinite, and the whole function is continuous. I love that because now what I can do is I can kind of compare these two ideas and see which one I like better. Maybe I just try like dropping in the number into the equation, right? They gave me the equation, I can use it. And look how they titled the first column, right? The limit of f of x as x approaches a. And then they say, okay, do f of a and then find the limit of a. So when they say x goes to 0 versus x goes to 2 versus x goes to 10, okay, so 0 is what I'll use first, 2 second, and then 10 third, right? Those are the a values that we're going to do. And with this first kind of empty column, they just say find f of a using the actual equation. Okay, so the first one, it says go to 0. Okay, then I'm just going to do f of 0 and see what I get. And this is not a place for you to be dropping this in and handwriting all of this arithmetic out. This is definitely like, let our path of least resistance take over here, and let's work smarter and not harder. You're going to see in calculus, I'm going to have to show you some long ways of doing things so that the shortcuts that I teach you actually work and make sense. Let's use shortcuts as often as we can. And you've got a graphing calculator, let's use it, right? You've got an ability to just like plug the function in and go to your table and like see what happens at 0, right? See what happens at 2, see what happens at 10, right? Maybe your table's already still set up so your independent values are blank, right? Because it's set to ask. So you can just 0, enter, 2, enter, 10, enter, and see what you get. The thing you have to know how to do though is type in absolute value. Right, so if you're going to y equals in your calculator, and so I would say probably from here on out, although we won't use them every day, we won't use them all day, having a calculator nearby is probably going to save you a whole lot of time. I want to do the arithmetic quickly if we can. My favorite way of getting to absolute value, there's two. My favorite way, your calculator's catalog is alphabetized. And so like you go to y equals, you type the 1/2, and okay, now all of a sudden I have to type absolute value. Well, absolute value is the first option in your catalog, which I think is like second 0 on your graphing calculator. It should just say ABS for absolute value. Older calculators will actually write out ABS, open parentheses, and then you just have to type in -2x plus 4 and then close parentheses around your absolute value. So you can put the -4 after. Newer calculators will actually draw the absolute value bars in there for you, and then you just type in whatever you need to for the inside, and then right arrow out to get there. But I'll save us a little bit of time because we're running a little short here. This is what we want to do. I just want to do f of 0, f of 2, and f of 10. Right, and I know this second one says, okay, go to 2 from the right. Well, that's like a whole limit thing. This is just evaluate the function, right? We should get, drop in 0, you'd get -2. Drop in 2, you'd get -4. I looked at the graph, I cheated. F of 10, well, I actually have to plug that one in. So let's see, -20, -16, so 16, 8, was that -4? No, 4, sorry. 4, right? Right, -20 plus 4, -16. So value of that +16, half of that is 8, 8 minus 4 is 4. Okay, cool. And what we see, what's so nice about functions that have infinite domains, that are continuous, is that the value of the function is exactly the same as the value of the limit. Like look at the graph, go to 0, right? Track the function as you approach 0 from the left, and as you approach 0 from the right, what y value are we getting close to? Again, I'm just gonna save us a little bit of time. I'm just gonna put the number in there, -2, right? go to 2, -4, right? No problem. Here's the problem. Go ahead, look at your graph and go to x equals 10. It's like over here somewhere, right? I can't see that. And so our graphs are limited, our functions are not. Okay? I can't answer that last one from the graph because I can't see x equals 10. But knowing that absolute value functions are continuous allows me to find limits really easily. Okay? And so I leave you with this. I leave you with this, and then I'll get you out of here. 2 things have to be true. When a function is defined, number 1, and continuous, 2, at a certain value for x, how can we find that limit analytically, like the hard way? How do we do it? The easy way. Direct substitution. You want to evaluate a limit at a function for a certain x value, and we know that it's defined there and continuous in the space nearby. Just drop that number in and see what you get, okay? What you're gonna see tomorrow, and I know I'm over my time a little bit, what we're gonna see tomorrow is I wanna just finish page 22 with you. I would like to do it with you, not necessarily on your own. So if you can come tomorrow, you can come to 2nd or 4th. I just wanna work through those 6 really quickly, like 15 minutes, right? If you have the time, so that we can kind of wrap things up, because as soon as we turn the page, we look at like direct substitution not working because now we're dividing by 0 or square, it's not, we get to some problems. So I would love to work with the bottom half of page 22 with you tomorrow if you can. If you can't, I think it would be a good idea for you to like watch the video before you actually try them out, or try them and then watch the video and see how you do. I'm happy either way, but if you want to join me for like 15 or 20 minutes tomorrow, either during 2nd or during 4th, I'm gonna be here. I'm gonna come in to kind of get up my room ready for Monday, where half the class will be here and half the class will be streaming in as we keep going. So I'll write this all out on Canvas so you know what to expect, but I'm good. You don't have anything you need to do for me for tomorrow. Just expect the bottom half of page 22 to happen tomorrow live if you want to join me, or do it on your own and just kind of watch the video so you feel like you're all caught up, ready to go for Monday. Okay? Thanks, everybody. See ya.
Thank you.
You're welcome.
Thanks.
Bye. You're welcome. You're welcome.
In the chart above,